So let's review just a little bit what we know about the propagation of electromagnetic radiation. One, we know the direction of wave travel is in the direction of the vector E crossed into B. And you can check that using the right-hand rule. You can pick any point here. How about this point? When the electric field points along the positive y-axis, at that instant the magnetic field points along the positive z-axis, and by rotating E into B using the right-hand rule, you can see that the wave is propagating in this direction. We also know that the magnitude of the electric field is equal to the speed of light multiplied by the magnitude of the magnetic field. So the number of volts per meter is always a much larger number than the number of Teslas associated with the electromagnetic radiation. And we also know that the speed of light is equal to 1 divided by the square root of the product of permittivity and permeability. What we would like is some sort of an equation that describes this propagation in terms of a wave. This is obviously some sort of sinusoidal behavior. Now, where exactly we place our origin is up to us. We can make a reference system where x equals 0 right here, or we can have a frame of reference where x equals 0 here, and then that just changes whether or not we have a graph of sine or we have a graph of cosine, right? Either way, sine or cosine can be described as sinusoidal. Let's animate this and see what it looks like as time progresses. So it's not just a variation in space. The electric field has a maximum value at different locations along the x-axis, but it's also varying in time. It doesn't hold its value at any position for any duration. Now we can freeze this probably for just a moment here. If we freeze it right there, then the electric field appears to be a graph of cosine. Let's do that one more time, right there. Yeah, the blue vectors is tracing out a graph of cosine, right? And there it is, back to animated. So let's just look at just the electric field. Let's ignore the magnetic field for a moment. Then if we capture a snapshot in time, just like we did, again, let's do one more snapshot in time. If I stop it right here, it looks like a graph of, right here it looks like a graph of sine. The electric field is oscillating like a sine wave. And if I stop it right here, it looks like cosine. So I've made a snapshot in time so that the electric field, with respect to position in space, plots out as a cosine wave. So we can say that E is equal to E maximum times cosine of what exactly? Well, how about this? We can say the distance from where the electric field, like right here, all we're saying is the electric field points up and has its greatest value. At this point in space, a couple centimeters down the line, the electric field still points up but has lesser and lesser value. At one location in space, for a moment in time, the electric field is 0 and the electric field starts to point the other way. So this is just an electric field that's oscillating in space, and the distance from one point of maximum electric field to another is known as the wavelength. Wavelength, we can give the symbol lambda. So back to here, that's also one wavelength. That means for every wavelength, every time x is equal to one wavelength, then the sinusoidal behavior starts over again, right? So I think we can say that the electric field is equal to a function of x. The farther down the line we go, we see variations in electric field. So somehow x needs to factor into this term. So what if we said electric field equals the maximum value times cosine of, let's just make up a constant, we'll call it k, times x. Now what would k have to be equal to? So for every full wavelength, that represents one cycle, right? By the time you've traveled one wavelength down the x-axis, you're back to picking up the beginning of the cycle again. And on it goes, and there we've traveled one more wavelength, and we're back to the starting point in our cycle. So every time x is equal to a wavelength, that corresponds to one cycle, which is the same thing as 2 pi. A cycle is 2 pi radians. So I think k must be equal to 2 pi radians for every wavelength. So that means the electric field is a function of x according to the equation. Just take whatever the maximum value for electric field is and multiply it times 2 pi over lambda multiplied by x. So let's say x is equal to 1/2 of a wavelength. So that would correspond to this point on the graph. You see it in red right here? Okay, so if we plug in half a wavelength for x, then we'd be taking the cosine of 2 pi over lambda times lambda over 2. Lambda would cancel, 2 would cancel, we'd be taking cosine of pi, and cosine of pi is -1, and so we'd be multiplying -1 times the maximum field, and this is why at that moment in time, the electric field would be -E. If we plug in just 1/4 of a wavelength for x, then 2 pi over lambda times lambda over 4, lambda cancels, and we're left with pi over 2, but the cosine of pi over 2 is equal to 0, which is why 1/4 of a wavelength down the line, the electric field is equal to 0. So this is a good description of how the electric field is oscillating with respect to position. Electric field with respect to position. It's just a cosine wave. However, as time goes by, we know it's going to propagate to the right. And so a little bit later in time, our graph is going to look something more like this. It's still going to have the same maximum and minimum value, but the whole graph will be shifted to the right as this wave propagates to the right. So how far is it shifted here? Well, we can just call that phi. Now, how would I write this? This means that the electric field at some point later, this is at time t equals 0, or at t naught, and then this graph in green, if we scribble out the original plot, then we're left with this graph in green that represents the electric field versus position at some later amount of time at t equals t naught plus dt, for example. So this amount of shift depends on how much time has elapsed. And E would then be equal to E maximum times cosine of kx. I think we have to say minus phi. Now think about why we say minus instead of plus. If you, if you just make a graph of cosine of theta, for example, let's compare that to theta. So when theta is 0, cosine is 1. When theta is pi over 2, cosine is 0. When theta is pi, cosine is -1, and so on. And then let's take another expression. Let's see, what if we did the cosine of theta plus 45 degrees? Then when theta is 0, 0 plus 45, the cosine of 45 degrees is rad 2 over 2, or 0.707, something like that. If we let theta equal pi over 2, then we got, how about this? Let me add some extra values in here. Make sure I explain this well. What if theta is 45 degrees? then cosine of theta is 0.707, but the cosine of theta plus 45 degrees would be the cosine of 90, which would give us 0. And then if we take 90 degrees, cosine of 90 gives us 0, and if we add 45 degrees to cosine of 90, now we get negative 0.707. And so if we were to graph cosine theta versus theta, we would have this graph. But if we make a graph of cosine of theta plus phi, then at 0 we have 0.707 instead of 1, right? So we've got a lesser value, and then at 45 degrees we have 0. So where this one at 0 was maximum, and at 45 degrees was 0.707, at 90 degrees is 0, this one at 90 degrees is some negative value, and so what we actually have is a graph that looks like cosine, but it's been shifted a little bit to the left. So I would urge you to see what would happen if you added another column to this table that represented cosine of theta minus 45 degrees. I can give you a prediction of what it's going to look like when you graph cosine of theta minus 45 versus theta. Instead of a cosine wave, you get something kind of like a cosine wave. It's just a cosine wave that's shifted a little bit to the right. So that's what's happening. If this is an electric field vector that's propagating to the right, then the phase shift involved must be a negative phase shift. In other words, when we allow this to animate in time, instead of just being a snapshot, if we can see two different graphs of electric field at two different moments in time, so this is still electric field varying in space, but the first one represents time t equals 0, and then the second graph represents t equals t naught plus dt, then electric field has to be described not only as a function of position, but also a function of time. So the electric field is some maximum value times cosine of kx minus a phase shift. Now, last I said we can call the phase shift phi, but thinking about that a little deeper, that phase shift must depend on how much time we allowed to elapse. If we let even more time go by, then it'll be shifted even farther to the right at a later moment in time. And it should depend on the frequency. The higher the frequency, the greater amount of shift it will have in some amount of time. So actually the phase shift is just equal to the product of the frequency and time. For example, let's just pick the position x equals 0 on our graph. In other words, instead of looking at the whole wave in its entirety, let's just set x equals 0 at this position, make a reference, and at this moment in time, the electric field is equal to its maximum value at the position x equals 0. Now, at another position x farther down the line, at a different one we call x prime, at that point E equals 0. But if we look at right at the origin at x equals 0, then we have an electric field that's equal to its maximum value. But as time goes by, if we were to animate this, well, let's just look. So, boom, at time t equals 0, and then we let time go by. And if you just look at how strong is the electric field just at the origin here, you can see the electric field is constantly changing. For a full cycle, it should go through a full 2 pi radians of change. So in other words, if we let x equal 0, then we get an expression for electric field only as a function of time. And E would be equal to Emax times cosine of negative omega t. I think omega must be 2 pi divided by the time period, so that if the period is equal to, or if the time happens to be equal to exactly one full period, then we'd be taking the cosine of negative 2 pi over t times t, and the cosine of negative 2 pi is equal to, 1. And so we're back to the electric field started out at the origin at its largest value, and then it starts to, in time, collapse and become lesser and lesser and lesser and 0, and then it starts to grow in the opposite direction. We're still not through a full cycle yet. It reverses and starts shrinking, and then it starts to grow in the opposite direction, and then right here at x equals 0, it's gone from its maximum value back to its maximum value again in one full period. So that makes sense. What if time is just equal to 1/2 a period? Then right here at the origin at x equals 0, the electric field starts out with its maximum value at time t equals 0, and then a little later it's shrinking, it's shrinking, it's shrinking, it starts growing in the reverse direction, and boom, this has been 1/2 of a cycle, and we would have the cosine of negative 2 pi over t times 1/2 of a period. The 2's cancel, the t's cancel, and we're taking the cosine of pi over 2, which gives us, gives us 0, right? So after, it doesn't give us pi over 2, it gives us pi, which is negative 1. I knew something was wrong there. Yeah, right. If we let t equal 1/2 a cycle, then the cosine of negative 2 pi over period times period over 2. Oh yeah, the 2 cancels out, the t cancels out. This is cosine of negative pi, which is negative 1. So we're saying the electric field has gone from being its maximum value at the origin to being its maximum negative value at the origin. So if we put this all together, the electric field as a function of both position and time is equal to some maximum value times the cosine of kx minus omega t. So the minus is telling us that it's propagating to the right. K is called the wave number sometimes, and that wave number is equal to 2 pi divided by the wavelength. We already have a name for omega. That's angular frequency, and omega is equal to 2 pi divided by period. Now, if the electromagnetic radiation was propagating to the left, then all we'd say is E is equal to E maximum times cosine of kx plus omega t. As long as we're picturing waves that are traveling to the right, then this is a good general expression for the way that the electric field oscillates in both position and time once we allow the electric field's motion to be animated. Okay. I'm not going to go through all that same argument again. It stands to reason that we could describe the magnetic field's oscillations independently as well. And it turns out, as you can see, wherever, at any given instant, if the electric field is at its maximum value, the magnetic field is also at its maximum value at that same time. Wherever the electric field is momentarily 0, the magnetic field is also momentarily 0. So they're cycling in phase with each other, just in different planes. So the strength of the magnetic field is equal to some maximum value, also times cosine of kx, minus omega t. Of course, I'm just representing magnitudes here. If we want to present these as vectors, then the electric field, well, how do we have it? Our electric field is pointing along the y-axis, and our magnetic field points along the z-axis. So if I have a x, y, z-axis, I'll remind you that a vector that's exactly 1 unit long along the x-axis is called I hat. A vector that's exactly 1 unit long along the y-axis is called j hat. And yeah, a vector 1 unit long along the z-axis is k hat. So because our electric field is oscillating along the y-axis, I can take the expression for the magnitude of the electric field, and if I just multiply it by 1, I haven't changed anything, but the 1 that I want to multiply it by is j hat, so that I can express that it's oscillating along the y-axis. So the vector E is equal to j hat times E maximum cosine of kx minus omega t if it's propagating to the right, and likewise the vector magnetic field is equal to k hat. It oscillates along the z-axis times B maximum times cosine of kx minus omega t. Okay, well, we took the long way to get there, but there we have it. This is the way that we can express how the electric and magnetic fields really are a sinusoidally oscillating phenomenon. And we'll use these expressions in the next couple video lessons in order to come up with a way to present what the instantaneous intensity is for electromagnetic radiation. Thanks for watching.